Um, Hello, everybody. First of all, I'd like to thank you all for attending this webinar. I can see this is a great platform to discuss different aspects of petroleum engineering. Before I start, I would like to highlight some points. When I was making this presentation, I tried to make it like more technical. Like you can find a theoretical approach in the internet, in the library, everywhere. So I wanted to make it like it's more interesting and more practical thing. And in fact, it is quite short to cover the whole thing in 1 or 2 hours. So I try to be like brief and highlighting the most important things that every petroleum engineer should know, and about like stimulation in general and acidizing in specific. Okay, so let's start. Today, I'll be talking about the well stimulation and covering different aspects of acidizing and the main challenges that we may face in the field operations. So let's start with the table of contents. Okay, like for no reason. Okay. As you can see here, we have the introduction. At first, we will start with the introduction, introducing what is stimulation, why do we need to do stimulation, and then we will pass through the roadmap. In the roadmap, we will actually pass through different problems in the reservoir engineer, and proposing solutions for different kind of problems. And we'll ask yourself, like, do we need to do stimulation or not? Okay, after following the roadmap, we will have the, um, the clear answer. And then we will go to the acidizing history and what's the treatment that usually is being done. And there is, I would not say like a new aspect, but about success definition is quite important, especially if you are work like for a company and your managers are always, asking about like what's the probability of success and stuff. Okay, and then we will end up with conclusions. Here we have the field life cycle. I always prefer to start with this chart. We can see like the main goal of the reservoir engineers. Starting with the exploration phase that involves the drilling of what we call the wildcat well of that first well. And then, I mean, that's what we call, exploration well. And then once the exploration well has encountered the hydrocarbons, there will be an effort is required to assess the potential of that find and also to assess the shape of the aerial extension of the field. And after that, we start with the development phase, which involves the infill drilling to increase the recovery factor until we reach the plateau rate, where should be like the optimum rate of the field. And this is exactly what's the main target of reservoir engineering, how to maintain the plateau period as much as possible by applying, different techniques, for example, stimulations and EUR. And finally, we end up with the field life, when the field or even wells, they start to decline and typically accompanied with water production until we reach the economic limit. So why am I doing this life cycle is about to know what is the main purpose of the reservoir engineer and what exactly makes us think about stimulation or other stuff. Stimulation is a treatment, or is any kind of treatment that performed to reservoir to enhance the productivity of the well, or it's about, restore or enhancement to the productivity of a well. And it's important to know that we can apply this stimulation, just after drilling, or it might be, after years of production. That's, depends on the policy or the methodology that your company or your organization follows. For example, in some companies in North Africa, they do as a job just after drilling. It's like an automatically thing. But in other companies, they don't do acid until they have like full analysis and full interpretation, and after, when the field is already matured. Mainly, the stimulation treatments fall into like two main groups. As you can see here, the hydro hydraulic fracture treatments, and matrix stimulation. For hydraulic fracturing treatments, is about performed above fracture pressure of the reservoir formation and create highly conductive flow path between the reservoir and the wellbore, while the matrix stimulation is designed to treat the near wellbore reservoir formation rather than going deeply into the formation. So of course the reservoir pressure or the treatment pressure will be lower than the fracture pressure. In fact, there are many problems that we are actually facing every day in the reservoir, and should probably know that sometimes it's not necessary to do acid or fracture for like to overcome these problems. Like there are some problems they could be solved by like other means, and we don't need to spend a lot of money just to overcome such problems. That's, for example, the sand control. We can control or prevent the migration of reservoir sand into the into the wellbore, by applying different techniques like gravel bank and stuff. And also we can control, yeah, there are so many methods have been raised to control water, or just sometimes we need to clean the wellbore. And later we will see like in details what kind of problems and how can we solve them actually. Okay, before we go in details, it's very important to diagnose the issue, as I told you before, that you have. For example, because well stimulation is not a cure for all the problems that you have. Here we have the roadmap that follows any issues that you may have and propose a specific solution for each problem. Okay, starting with production test. At first, we need to do production test. This is the best way to know if you have a problem. Assuming this is like a mature field, there will be three possible outcomes. As you can see here, this is the liquid decline, no flow at surface, and if you are lucky, you will see Shini, you will see no liquid decline. Theoretically, the liquid should remain constant because because of many reasons, you might have a decline in the liquid. Okay, and this is the main purpose of roadmap, to diagnose why do we have a decline in the liquid. And sometimes some wells, they don't show flow at surface, even though the offset wells producing properly. So in a minute, you will see like why do we have a liquid decline and why do we have no flow at surface, even though like there is good potential of that wells. So we will go through each one of them and start with no liquid decline. If we have no liquid decline, that means the liquid rate is constant. So we need to check further the oil. Is it constant or not? If there is no oil decline, that means we are in a safe side. I mean, everything is okay. But in the second option, if there is an oil decline, that's pretty much will be due to water production, because of relative permeability change issue. So in that thing, we need we need to diagnose the source of water. There are many techniques have been proposed to know the source of water that you have. So one of these techniques are the PLT, or the production logging tool. It tells you exactly the contribution of produced fluid for each interval. And also you can use the tracer and the injected water to follow the tracer and see when and where it's being produced. So all these techniques are being used to know the source of water. And also there are like a diagnostic plot called Chang graph that also can identify the watered out zones, and it tells you whether you have a channeling or the water is coming from bottom, or what we call it coning. Obviously, the water coning usually occurs when there is excessive liquid production, when the vertical communication among the layers is very good, or the lower perforation is very close to the free water level. So in that case, we might need to do what we call it water shut-off, just by isolating the watered out zones. And if the problem, if the case is the problem is about channeling. So in that case, we need to check exactly the water is coming from in which injection. So that's why we might need to do like an interference test between injector and producer. And up onto that, we might decide that to close water injection, specific water injection, and with keeping an eye on the reservoir pressure in the optimum voidage replacement ratio. Okay, so this is all for the first scenario when we have no liquid decline. And let's go back to the first roadmap and follow the second option, which is either we have liquid decline rate or no flow at surface. Here, as a reservoir engineer, we should be aware of all the operational fields that took place, starting from drilling, workover, history. I mean, all these things are important for us because, here is, we will review any sort of damage that were introduced to the reservoir. And if you click here, that will bring us to the chart of damage assessment. Because of, presentation time is not like, it's going to take like for a long time, so we cannot go through each one of them. I will, highlight the main things here. Obviously, we have two kind of sort of damage that we might have in our reservoirs. The first one is natural damage, and the second is induced damage. And most likely to have both type of damages in our reservoirs. So natural damage, usually due to production. For example, in unconsolidated sandstone reservoirs with high pressure drawdown is typically to produce sands and therefore blocks the perforations and harming the integrity of your artificial lift, let's say ESP bomb. Or another issue is the clay swelling due to water production, which definitely reduces the permeability of the reservoirs. Many times the damage is induced in form of drilling. Like, it's no need to mention that these cases of mud losses that causes invasions of solids and filtrate into the reservoir, which pretty much blocks the flow path. So the flow will be either restricted or prevented from flowing, depends on the overbalance pressure that was, occurred. And surprisingly, it might reach to a huge difference from mud pressure and reservoir pressure. So another type of damage of the damage due to perforation. Under the best conditions, the perforation will destroy the original permeability. That it could be reached up to 60% of the original permeability, and also yields a compacted porosities. In addition to that, the perforation, the number of shots is not, if it's not like well optimized, a new damage will be, introduced due to what we call convergence skin. One of these problems or formation damage is, the damage due to injection. Once we inject water, we are actually introducing a new flow to the reservoir with different pressure and temperature, which causes, a pH change. And such kind of change create a scale build-up and reduces the permeability. So all sort of damage, no matter if it's a natural damage or induced damage, all these things are reducing the productivity of the well. So we always need to think how to remove such kind of damage by applying different techniques, different sort of stimulations to our reservoirs. So let's go back to our roadmap. So after reviewing the drilling history and shed the light on the damage that you have, now it's time to know whether the problem is a mechanical problem or a reservoir problem. Maybe some of you like is wondering why do we see like this, and we are talking about simulation. The thing is quite important to know the source of your problem, so you will it will be very easy for you to understand the simulation and understand why are we doing simulation. If it's like a mechanical issue, that will include the well integrity and the artificial lift. uh, if we check like we can check the well integrity like by slick line drifting to the total depth, and check the perforations if they are blocked or not due to sand fill or any other mechanical things. And we need to check the cement bond through CBL and VDL logs to help to detect if there is any potential casing leakage or flow behind casing that harms the or affecting the wellbore productivity. And of course, we can do that also by applying PLT, and PLT has got different advantages, so it can help you with making sure of well integrity as well. So after checking the well integrity, then we go to the artificial problem, whether ESP or gas lift. With the ESP, there are usually tri-sensors, which give you a very good idea about the mechanical or reservoir energy via BWF or flowing bottom hole pressures. And of course, the higher drawdown, the high expected to be damaged. Okay. Um, Another thing for ESP is a dynamic fluid level. Dynamic fluid level can, gives you an idea if it's a mechanical problem, because for the design DFL, there should be like a specific number, and if this is of the real numbers shallower than what it should be, so you can imagine that is a mechanical problem, and sometimes you need to change the design or change the type of bomb. Okay, so if we guarantee this is not a mechanical problem, so we start thinking about reservoir issue. Before doing anything, we need to review all the petrophysical properties. Um, the petrophysical properties that includes the porosity, permeability through conventional core analysis and RFT data, and also will logs of the well by compare compare the issued wells to the offset wells, and that's to evaluate the potential of the well, and we see is this well really promising to spend the time on that well or not. And then review the reservoir energy by checking downhole pressure if this like an optimum pressure or not. Okay. Sometimes the aquifer is not enough to support the reservoir pressure, or sometimes there is no aquifer, but the injection or water flooding that is being used is not enough to maintain the reservoir pressure at the optimum pressure. Okay, so that's why we might need just to think about, water injection, water flooding, instead of, doing stimulation. I will have like a question for you, and I will not give you an answer today. We can discuss it for tomorrow. The question is, and of course you can write your answers like in a comments, or we can discuss it, later. So the question is, what is the optimum reservoir pressure? So how can we say this is the optimum pressure of the field? So feel free to write your comments. And of course, tomorrow at this time, we will, discuss it together. So if we make sure that all these things, like everything is okay, now and only now, we should think about reservoir integrity. That lead us to investigate the skin analysis and the productivity index. Okay. We can visit here like a brief chart. The skin effect, as interpreted from pressure transient analysis, is aggregated of several factors of near wellbore region of the reservoir. Like a formation damage is one of the component of the total skin effect. It's quite important, and like no many people know that, it's quite important to differentiate between skin factor and skin effect. Skin factor is a dimensionless number that distorts the physics of fluid flow in porous media. However, the skin effect, is about exaggerating the drawdown required to produce at a given rate. So the magnitude of skin factor could be, misleading because many times we have the same pressure drop with different permeabilities. Therefore, we must be sure that the source of skin is due to damage. So, maybe someone tells you we have a high number of skin value, and that means we have like damage. This is sometimes incorrect. That's why we need to differentiate. We need to know the source behind this big value of skin. In fact, there are like so many calculations that we can do that help us to diagnose the skin type. Maybe in other events, we can arrange for other or for a long webinar, so we can talk how can we know exactly what's the source of skin that we have. So let's go back to the roadmap. Um, Generally speaking, if the damage is due to partial completion, so let's say there are like two main drivers to make high number of skin. So this is the let's say the skin is due to partial completion. Okay, so we can do something called reperforation. Just be aware of the distance to free water level and the gas oil contact if you have, to avoid early water breakthrough, and also to avoid gas and water coning. Okay, so after all, you can just do the reperforations and check the productivity index. It might increase and everything is going to be all right. Okay, if the case skin is due to damage, so now you can we need to do stimulation. And as I said, like there are two type of stimulations, fracturing and acidizing. And if you have noticed that, like for the whole roadmap from the very beginning, I didn't mention stimulation at all, and we have like lots of problems. So that's why any reservoir engineer or any production engineer, and he's like assigned to do the acid job, he should be careful with exactly the problem that he's facing. So that's why we propose the best solutions. So as a rule of thumb, if we have a high permeability and good original petrophysical properties, it's better to go with acid job. While if we have like a tight formations, the first thing comes to your mind is the hydraulic fractures. Okay, so this is a very general overview. And now let's have a look at matrix treatment. Acidizing is not exactly a new technology. The first acid treatment ever done was 1895 by the Ohio Oil Company, and I'm not pretty sure about the where it was, but I guess it was in Ohio City. It was fairly successful and had a hydrochloric acid treatment, but they had a corrosion problems. They didn't pay attention to the corrosive materials. So in the essence, they forgot the iron steel is soluble in hydrochloric acid, and they experienced a severe problems in the tubing. And it took them almost like another 40 years before the second acid would be done. And they were, corrosion inhibitors and developed so far. It was about like 1932, and they managed to overcome the problem of the corrosion materials. It developed later on. The main drive came actually in 1980s when it was extensive research done to improve our theoretical understanding, and as a result, we have new fluid and assist completions. And of late, essentially in this century, really started computerized design and execution support of acidizing treatment. As you can see here in this picture of like the 30 early of acid treatment, for those who are aware of it, it says here already the name of Dowell. You know, it's a company that was, you know, set up by Dowell Chemicals, and later on was taken over by Schlumberger, and for a while was known as Dowell Schlumberger, and now, you know, the Dowell has just disappeared, and only, you know, the Schlumberger is exist. So you can see here the equipment is quite simple. As you can see, the pump track little host and is connected to the wellhead. Okay, basically, there are three types of acid treatments. You know, it depends on the level of the damage and how much the depth of penetration like is needed to stimulate the well. In acid washing, uh, uh, sorry for the interruption. In acid washing, the objective is simply tubular and the wellbore cleaning. So the treatment of the formation is not intended actually, and the acid washing is most often performed to clean out the scale and, you know, the other anything that restricting the flow path to the wellbore. In matrix acidizing, the acid treatment is injected at matrix pressures, or, you know, at below fracture pressure, and in fracture acidizing, uh, like all the acid treatment is significantly bumped at, you know, over fracturing pressure. Um, okay. Before we start talking about like detailed acid treatment, it's essential to understand some concept about acid treatment. Once we decide like to do the matrix acid treatment, the first thing we do is about, you know, making sure that the stimulation will not add or will not introduce a new damage to the reservoir. So the first test we actually do is a compatibility test between the reservoir fluid and stimulation fluids. So why do we do this? Like, what's the main objective of compatibility? Because due to the tendency of these combinations to causing damage to the wellbore, you know, if the compatibility is not ensured. And then we have like a solubility test, understanding how the reservoir rock may react to the acid injection. Like is quite important to ensure that the damage to the reservoir formation does not occur, and also to help understanding if the permeability could be improved or not, which is which is the most important thing in this story. So at first, the blocks or the core block is were measured for porosity, density, seismic wave velocity, and also the permeability as well. And then the sample's exposure to the hydrochloric acid, and then followed by hydrofluoric acid. And after that, we observe any physical change that occurred in the core block after acid exposure. And then, and also there is a corrosion test, you know, to avoid any harming to the well integrity and to avoid any corrosions that may occur while doing acidizing. As you can see here, like and later on, like I'm not sure if it's today or tomorrow, we will talk in details about, you know, what type exactly of, you know, additives and whatnot, about, you know, corrosions and stuff. Um, as you can see here, the acid design should not be the same like for all the rock types, because I would be like more confident with if the rock formation is carbonate than sandstone. Since the sandstone, like you need to be very, very careful with your design, and then in the next slide you will know like why do we need to be careful with sandstone formations. And then talking about additives, the main idea behind additives is to get over the suspected issue that may arise while injection acid. For example, corrosion inhibitors to prevent corrosions, diverters in case of heterogeneous reservoir when we have different permeabilities and we want to make sure that the acid is injected in the right place. So that's why we do some additives like diverter to make better placement to the acid injection. Okay, it's quite important to highlight that sandstone or reservoir consists of different clay minerals. Okay, this is very essential thing, and it's very quite important to know it, to know what kind of clay minerals that you have. And according to that clay minerals, you will decide or you will make your recipe ready to react with these cementing materials. Some of these clay minerals are like colonite, cementite, illite, like there are so many of them, and these are the most common one. And these clay minerals highly affected the formation damage during the stimulation operation. So we have to be aware of all the clay minerals that we have. The interactions of clay and other minerals with fresh water and strong hydrochloric could result in dissolution or precipitation, sometimes plugging, clay swelling, and fine migrations, and all these things will introduce a new formation damage. So um, before commencing any acidizing job, try to understand what are the clay minerals, and according to that should be translated to the recipe of the design. So everything is going to be, smooth, and everything is gonna be okay. So in sandstone formation, the matrix acidizing treatment should be designed primarily to remove or dissolve the damage or plugging in the perforations or in the formation near the well bore. So as you can see here, theoretically, acid flows through the pore system, dissolving solids and fines that exist in the pore throats, and then restrict the fluid flow. If there's like one thing you should know, that in sandstone treatment, that the sandstone acidizing treatment has a chance like for success only if the acid removal plugging or formation damage is present. Otherwise, you will introduce a new damage to the reservoir, and unfortunately, you will get fire. So that's why you should understand if there is a damage or not. And if there is not a damage, if there's no damage in the reservoir, in the sandstone formation, try not to introduce acidizing. Try to find any other solution, because you will like add a new damage to the reservoir, and this is going to be good for you or your company and so on. So like that's why I want to make this presentation, to define the problem, and like all the time I give a strong weight to define a problem before decide anything. Okay, so as you can see here, so let's see how it looks like in sandstone reservoirs. In sandstone, you really want to dissolve some, sort of damage, whatever the damage has been, created by. It could be created by drilling, or fluids that's being produced, or any sort of chemical interactions that with the fluids that will be like between the fluid and the formation. Things like clay swelling, fine movements, etc. And this is like indicated here, like in a little black particles. And the ones who love, chemistry, now we will start talking about like the main interactions, the main reactions that we have in sandstone formations. In sandstone acidizing treatment, you need a mix of hydrochloric and hydrofluoric acid. So only in the sandstone we use hydrofluoric acid. As we will see later, for the carbonate, we're not going to need for hydrofluoric acid. Okay. In the old days, people started with 12% of hydrochloric and 3% of hydrofluoric, and it was like regular mud acid. Actually, this term was like a Schlumberger term, and if you are dealing with Halliburton, they would say like hydrofluoric acid instead of like mud acid, because but exactly they are exactly the same, just in terms of terminologies. Once we introduce the mud acid to the sandstone formation, the hydrochloric acid would be hardly spent, but almost all the hydrofluoric acid would go away. So the end will result with have something like 10% of hydrochloric acid and 0.1% of hydrofluoric acid. And also will compound of ammonia and silicon fluorides, and that's what we call the primary spending of hydrofluoric acid. And at the very beginning, people say that is nothing else is going to happen. So this is what you have. So you're just going to dissolve the thing, and your happy life. Your managers are happy that you stimulated something. But it turned out that um, that it has been found that there is a second stage of hydrochloric spending, and in this stage high percentage of hydrochloric acid is left, and you end up with 4% of hydrochloric acid, and the same percentage 0.1% of hydrofluoric acid, and the large amount of aluminum fluoride, and unfortunately the silicon and fluorosilicate will precipitate. So the precipitation of this insoluble material is what exactly adding the new damage to the reservoir. So if anybody tells you like we are doing, we are stimulating, and this could be like, how can we exactly, determine the exact percentage of hydrochloric and hydrofluoric acid? Okay. I will tell you, in sandstone, everything is critical. The volume of acid, the recipe of acid, all these things should be, optimized very carefully. And that should be based on, the diameter, or like the investigation, the depth of invasion that have been occurred to your reservoirs. And also depends on the cementing materials that you have. So after the second reaction, like after first reaction, whereas the hydrochloric, most of hydrochloric was like remained, and then precipitation of, if in the second reaction we have precipitation of insoluble materials, and then it turned out, and even more, like the tertiary spending stage, that what we call it. This is like 4% of hydrochloric acid and 0.1% of hydrofluoric would be reacting even further to spend, all the hydrochloric and hydrofluoric, and you end up with the solution that is very high with, aluminum fluoride compounds, and in fact, you will have a risk of precipitating and scaling in the whirlpool. So here the thing is, like there are so many techniques have been used to control the volume, and there are so many techniques have been done to exactly place the fluid in the right interval that you think that is quite damaged. So this story of acid is not gonna be like a simple story, but I think I should stop here, because like it's been said that whenever the presentation exceeds the 30-minute, like up to maximum 45 minutes, the the comprehension will decrease, and the efficiency of the presentation is going to decrease as well. So I propose to stop here, and